All right. Good morning, everyone. Thanks for joining me. My name's David Smith. I don't know about you, but I thought the keynote this morning was just a really, really awesome vision of modern BI. You know, this whole idea that rather than using a BI system to look backwards in time, do summaries and tables and visualizations of things that have already happened, this whole idea with modern BI is to be able to take it to action by incorporating predictions and recommendations and selections that come from predictive analytics so that we know what to do based on what we've learned from the past to be able to anticipate the future and then take action. So my goal in my presentation today is to take you really behind the scenes of what makes all that work. And that's predictive modeling, happening in real time, often with big data. At Microsoft, I'm responsible for working with an open source community called the R community. R is a programming language which is used by data scientists to build predictive models like this. And I'm a data scientist myself, and as I've been working with the community who's been implementing many of these underlying techniques and working with customers who have then deployed those techniques into real-time applications to make real differences, to be able to learn from these masses of big data that they've stored and then take action on them. I'm going to share with you some of those examples and take you behind the scenes to show you how they're made. Now, I've been working with statistics and data science and predictive modeling for a long time. For a long time, it was really more of a back office operation, happened in dark rooms. But now it's everywhere. You can't escape. I'm going to skip over that slide. You can't escape predictive modeling. It's everywhere. You'll see it every time you visit a website, for example. I visited this website yesterday. There's an ad. It's an ad for a car. It happens to be a pretty cool car. It's one that I might like to have. This is an ad that was pretty well targeted towards me as a consumer visiting a website. And as you probably will know, behind that ad is a massive quantity of data and predictive analytics that led to that particular ad being selected for me. A lot of the data that was used to select that ad for me is actually visible to you right there on that screen. For example, it's a technology website. That gives you a little bit of information about me and the kinds of things that I might like. I'm visiting that website using a browser. It happens to be Chrome running on Chrome running on Windows, which gives you a little bit more information about me as a person and my choices of technology. I'm logged in to an account using that browser, so I have a whole set of information, particularly cookies, that are associated with me that's available to the advertising technology as it chooses which ad to present to me. Of course, many of those cookies come from social media data. I'm quite active on various forms of social media, and there's quite a lot of data available to this particular advertising network from my activity on Facebook and LinkedIn and Twitter that gives them even more information about what I might be interested in purchasing or knowing more about. And then combine all of that real-time data about me and my history and my experiences that come just from the browsing session with data that comes from advertising networks, data that comes from demographic agencies which can purchase information about me and my interests and my hobbies that again can further inform what particular ad is going to appear on this website. So that's just one example of myriads that you'll encounter on your day-to-day life of predictive analytics in action. But what I want to show you today is a bit of information about how those models are built. The basic idea is a predictive analytics model. And what we want to do is start with things we know, user inputs, my name, my address, my date of birth, my history, my browsing history, my friends network. And then combine that with what I'm going to call here scoring rules, just a very simple algorithm which takes the information that's known about me and my session and my action in real time, and then generates what we're going to call scores or classes. And this is the thing that in the previous example is the ad that has been selected to show to me at that particular point of time on that website. Or it might be something like a recommendation of a product or a forecast of a financial quality. Whatever it is we want to predict or select is generated from stuff we know now, those factors, through scoring rules to generate those predictions and selections. Big data is, of course, a big part of this process. We use a lot of historical information. We learn from the past about previous actions that generated outcomes, where we knew what the appropriate prediction or selection or recommendation should have been, and then look for patterns in that historical data to generate those scoring rules. And I'm going to show you how that works in just a moment. Before I do, though, let me show you just a few other predictive analytics applications to set the scene. The finance industry, of course, was probably way ahead of the game outside of the research industry in using predictive analytics models. If you've ever applied for a loan, there was a whole bunch of predictive analytics involved in there. Predictive analytics was used to generate your credit score. Predictive analytics was used to determine whether or not you qualified for a loan. And if you did qualify a loan, it was used to determine what, from the bank's point of view, the appropriate interest rate was to give you for that loan to match the risk level associated with you as a particular consumer. That's been going on for a long, long time. The financial industry has gotten much, 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 much more sophisticated when it comes to using predictive analytics models. On the right-hand side of the screen there is an example that comes from an investment bank that's using what we've learned from social networks like Facebook about how people interact with each other, but instead applying it to companies. If a bank can understand how a company is interrelated with other companies through the parts that it purchases, or the investments that it's had with those companies, or the financial ties it has with other companies, banks can use that information to further understand the risk associated with a particular company because of the risk associated with the companies that it interacts with, and thereby create a much more accurate assessment of the value of a portfolio of many companies, and equally importantly, the risk associated with that portfolio is when, in today's modern financial world, so many companies are all interdependent. Here's another example, a great local example. I don't know if anybody's ever used Zillow to go in and have a look at, I can see a lot of nodding heads out there, have a look at the value of their house. That's another great example of a predictive model. Zillow's a real leader in this, taking historical data of house sales, combining that with information about those houses, not just how big they are and how many bathrooms they have, but also information like crime data around the area, which can also influence the value of that house. So taking a big data set, looking at historical values of house sales, combining that with data about those houses, Zillow can use a predictive model, they call it their Zestimate, to infer from the past what the value was of houses sold associated with their various data, so that when you're looking at a house that's brand new on the market, you can take its attributes, put it through the Zestimate, that predictive model, and get a new estimate for what Zillow thinks that house ought to be worth and what you might consider buying it for, or in other cases, renting it. We use predictive models a lot at Microsoft. As we saw in the keynote this morning, we generate a lot of data internally, not just about our flying habits, but also in support of the operations of the Azure cloud, which, as you heard this morning, is the biggest worldwide cloud computing operation and generates massive amounts of data, which we would like to make useful predictions for. The Azure cloud is growing rapidly, adding new servers within existing data centers, but also adding new data centers around the world. So our operations team needs to be able to forecast how much more RAM chips they need to buy, how many more hard disks they need to buy, how much more electrical provisioning they need in all of those environments for which they use predictive modeling. Specifically, they use a forecasting technique very similar to the forecasting you saw in Excel in the keynote this morning. Another use of predictive analytics within Azure is for security, identifying alerts that happen when there are unusual transactions across the network or unusual login events. And again, it's the same idea, using data from the past, having a look at real attempts into the Azure cloud, being able to have a look at the characteristics and data associated with those attempts, so that when new login attempts are occurred, we can flag them as possibly malicious or not and act accordingly. And finally, this is getting really to the forefront of what we can do with data science today. This was actually from a demo that was given at the Build conference last year, where Joseph Soros, one of the CVPs here at Microsoft, plugged in a USB stick containing his own DNA which he had analyzed by 23andMe, plugged it into a Windows Phone application, and in real time, that data was analyzed, compared with a historical database of genetic diseases, and shown directly on his phone what genetic diseases he was predisposed to because of his own DNA, and comparing that with an analysis of the population at large. This is another example of predictive analytics working in a real-time environment. Now, what do all of these applications have in common? First of all, they're running in real time. We're visiting a website, we're using an application, we're monitoring operations in real time, and we need to react in real time. Many, if not all of these applications involve big data, massive databases of house sales, massive databases of genetic diseases, and looking at the history of that data allows us to learn and make predictions from it. And that ultimately is what we're doing. We're building these predictive analytic models that let us learn from the big data and make those predictions in real time. Now, I'm going to start using a lot of buzzwords at this point, because I'm going to tell you about how to build these real-time predictive analytics applications with the big data. But I want to explain to you what those buzzwords mean, at least in my opinion. And I'm going to start with big data. Big data is probably the buzzword when it comes to this particular segment of the industry. There are lots of definitions of it. I like to use an analogy. I like to think of big data as crude oil, or like crude oil in the sense that crude oil is hard to get at, it's messy, it's full of contaminants, it's expensive to extract, it's expensive to move around. But when you refine crude oil, when you boil it down, when you refine it, when you rearrange it, chemically in this case, you get something useful. You get data that has value. So think of big data as not the stuff that you and I, or many people typically work with in something like Power BI. Big data is really the source material that needs to go through a refinement and an extraction process before it's useful to be used in a predictive analytics environment. It's the source. So that leads us to the 5 stages of putting together a predictive analytics application and deploying it into a real-time environment. First is working with that big data and distilling it down in some sense so it's ready for a data scientist to analyze. Once we've gone through that extraction and distillation process, we need to build a predictive model. This is something a data scientist does, is to develop a predictive model on that what's been extracted from the big data, and then train that predictive model to generate the scoring rules that we saw earlier on. Once we've generated those scoring rules, we need to deploy them into some kind of a real-time system where we can plug in data that comes from an action and generate that recommendation in real time. And that becomes real when somebody actually consumes the results from that scoring model, when they interact with an app or a website that has predictive analytics built in. Things are working at this point, but it's not the end of the story because the world is not static. We're continually generating more data, and the environments in which that data is generated and the responses of the actors, the people, and the machines and the Internet of Things, and how that responds to that data changes over time. So we need to periodically refresh our models, go all the way back, sometimes to the very beginning, to rebuild those models to keep them fresh and make sure their predictions continue to be valid. So let's start with step 1, which is the data distillation process. You've probably heard a lot about unstructured data. There are lots of places where we can put things like log files coming out of sensor systems, sensor streams coming out of the Internet of Things, language data, emails, documents, social media messages, any kind of text, can all be put together into an unstructured data system like Hadoop, HD Insights, a data warehouse. But as I mentioned earlier on, it's not really usable yet at this point. It's like that crude oil. So we have to go through a distillation process and extract out the data from its core systems, which may be a disparate set of systems, and put them into a nice, regular, unstructured data store. Now that often involves a lot of data cleaning, not just simple things like eliminating outliers and obvious errors in the data. There's often aggregation that needs to be done, especially in the financial world, while we have millisecond level data. We can't often work with millisecond level data when it comes down to building the predictive models. So we need to aggregate it down into minutes or hours or days or months or years, depending on the scope of our particular prediction that we want to make. Once we have that data distilled down and put into an unstructured data store, again, that could be something like Hadoop or a data warehouse where the data is nice and regularized and cleaned up. We then go through another set of processes, which is extracting it out into a structured data environment ready for the predictive modeling purpose. That's because when we're at this unstructured data store in the middle, we're still dealing with very, very large amounts of data, and almost certainly much more than we need when it comes to building a predictive model. So before we get to the predictive modeling phase, we'll do things like summary analysis, aggregation, binning, bucketing, cleaning of that data and store it in a nice regular table, something with rows and columns that you'd be familiar with from Excel or SQL. Once we have that structured data with the rows and the columns, we're ready to begin our predictive modeling analysis. We saw a good example of that, by the way, in the keynote this morning. You saw we started with text data, it was social media data, and then we provide some sentiment analysis to that. Now, just from a mathematical point of view, we can't build a predictive model on tweets, but we can build a predictive model on the sentiment associated with that tweet. That's a very simple number, sentiment of 0 up to sentiment of 9, that we can put into a mathematical model. So while we might have tweets living in our unstructured data store, we do our sentiment analysis and put the sentiments into the structured data, and that's what we'll actually be using in our analysis phase. Once we have our nice structured data, this is where the data scientists get involved, and we start building our predictive models and training them. As I said earlier on, we start with things we know, but in this case, it's things we know from our historical data. We're not yet into the real-time environment. We call those factors. That could be things like in the marketing example, my user ID, the browser I'm using. Oh, my mistake. Not my user ID, historical data from people who have used those applications in the past and their user ID, their browser, what time and date they interacted with the website, where they were from the geodata, all of their previous purchases, their friend data. All this information that might, in the marketing example, lead me to choose a particular ad to show to them. We're also going to combine that with the actual outcomes we have from history, like, for example, which product was actually purchased, which we're going to use to find patterns in with the data. So let's summarize that and just call those factors any known information. As I said, we're going to combine that with the things we actually know from history, which products they generated, which product they purchased, which offer they actually took, so we can then generate ultimately for the future the product that might be of the most interest or the offer that might generate the best sale in the future. In the finance thing, or in the Zillow case, that was the forecast sale value of the house. And in a financial setting, that might be something like the optimal bid. That's our prediction or selection. And as I mentioned, what we need to do is generate some rules that translate what we will know in the future with what we want to predict in the future. And we're going to use our historical structured data that we generated from the previous step to do that. That's going to generate our scoring rules. And our data scientists are going to employ lots of techniques that you may have heard of. They might use decision trees or logistic regression or neural networks or k-means clustering, ensemble models, any number of techniques, or perhaps even several of those, and compare which one does best in order to generate those scoring rules. There are many applications available to you, or to data scientists specifically, that can convert that historical data into scoring rules using those techniques. The one that I'm most familiar with is R. And I'll give you a little bit more information about R later on in the talk. So let's talk a little about the process that a data scientist uses to take that historical data with the known factors and the known incomes and generate those scoring rules. It's a process. It can take days sometimes. With a data scientist looking at the data that lives in the structured database, selecting which variables might be important, doing even more sampling and more aggregation sometimes, transforming variables. Often the variables you get right out of the data aren't ready for analysis from a mathematical perspective. Fitting those k-means clustering models or those regression models and then comparing those models to other ones to refine the one that works the best. compare the results of that model with historical data. Just basically pretend you've gone back in time, fit that model, and then we already have data that we've collected in history. Have a look at how that model would have performed had we done it at that time. You saw an example of that in the keynote this morning when we went back a little bit in time to do our forecasts, and we saw that they were well aligned with what we actually saw in the real world, so that was a pretty good model. Data scientists do that same thing every day. And then they're not done. They go through that process again and again and again, continually refining that model to get one that they feel is going to give the best actual predictions, give me the best ad that's the one I'm most likely to click on, give me the best estimate of a housing price, which is going to most closely match the actual price when the house does actually sell. But the ultimate outcome of this process is the predictive model. And I want to re-emphasize here that we're not yet in the real-time world. This is a data scientist working offline typically to build up these scoring rules that ultimately will go into the real-time system. This can take a long time, as I mentioned, especially when we're working with big data. But even though we're not in the real-time environment, time is important here. Because every time a data scientist goes around that cycle, the model gets better. The predictions get better. The model gets more accurate. And if it takes, for example, 8 hours to go around one of those cycles, that basically means the data scientist can only iterate once a day, unless they happen to be burning the midnight oil. So the more we can cut down the time it takes to go around that loop, the more iterations data scientists have to refine that model, and ultimately, the best predictions we will have. That becomes really important in the big data domain. Now that data scientists are working with gigabytes, occasionally terabytes of data to build up these predictive models. If you need to move that data around, it becomes a big deal. Data has weight. Trying to move hundreds of terabytes of data across a network connection can take minutes, maybe hours if you're in some kind of data center where you have a limited connection. And that does happen. I've seen it happen myself. So when it comes to fitting these predictive models, it's really important from the data scientist point of view that you don't have to move the data anywhere. So you can cut out that data transfer time. So these new technologies we have, like in SQL Server 2016, where you can fit a predictive model using R on data that lives in the database without having to move it. Or with Hadoop or HD Insights, where you can leave the data in the Hadoop system, and again, run the data where it sits and do the analysis where it sits without having to move it into another environment for analysis, is really, really important in cutting down the time to go around that cycle and ultimately gives us much more powerful predictive models. So the data scientist has done their thing. They've generated a set of scoring rules. Scoring rules are pretty simple. It could be something as simple as just a threshold. If this sensor goes above minus 0.75, then signal alert, otherwise don't signal alert. Very simple to code up. They can be more complex than that when we have lots of variables, like all of those variables that I had about me when I was visiting a website. They need to be fed into those scoring rules. And ultimately, these need to be implemented in some kind of real-time system that can translate the incoming data through the scoring rules to generate the recommendations. I'm not going to go into this in too much detail. This is really sort of more in the IT domain when this happens, but for very simple scoring rules, you can actually do it directly in a database. This is a lookup. Given variables A, B, and C, just permute all possible variables of A, B, and C, generate what score we would have had, and we could just look it up in a table. That's a really easy way of doing it. It's not always possible, either because we don't know all the possible values in advance, or there are just so many combinations that you can't possibly calculate them all ahead of time. More often, you write code to generate scoring rules. There's a protocol called PMML, which many data scientists can use. The output from their predictive model can be transformed into PMML, which automatically essentially generates those scoring rules in many real-time environments. You can use SQL. You can write the code in SQL that does those transformations, or use some kind of pre-configured rules engine. Or you can just have a programmer convert those scoring rules into code in a language like C++ or Java or R. Whatever it is, the process is the same. You've got a system that can convert input data from the real-time environment into those scores and predictions through those scoring rules. And then it gets deployed into the real-time system. This is where the rubber really hits the road. We've got our real-time data. That becomes our factors. These are our things that are known at the time of the event. We'll plug those into the scoring rules. A modern architecture for doing that, of course, is to do that through a web services API. Either have a local scoring server running in your local environment, or even doing that through the cloud, as we saw in a couple of the examples I gave earlier on. From that real-time data, our factors, through the scores, we generate our prediction, our score, our recommendation, and then that gets displayed somehow in the application UI, either as a particular web that I see in my website, or as a table of diseases that I might have based on the real-time DNA that I pass through this system. One thing I want to mention here is that we are no longer in the big data world at this point. The only data we're dealing with in the real-time environment is the data that's generated by that one user at that one time, typically pretty small. We've got our scoring rules, pretty small amount of code, and we generate our score, which is often just one number, add number 3, 4, 5, 6. All the big data that we started with, the crude oil, the structured data that we refined it down into, the data table that the data scientist was working with, none of that is relevant anymore. The only thing that we care about in the real-time environment is those scoring rules that was generated from that process. And lastly, I mentioned time moves on. Things change, new users enter the system, new products enter the system. Every now and again, we've got to redo this process to make sure that our models stay fresh. And how do we do that? Well, we have an advantage, and that is that as soon as somebody interacts with that real-time predictive analytics system, we know what the actual outcome should have been, or actual outcome was, compared to what we predicted it to be from the model. That ad popped up on my screen. Did I not click on that ad? It was put on the screen with the hope that I would click on it. It was predicted that was the best ad that could be shown to me, that I might click on that ad. But the system knows at that point whether or not I did or did not click on that ad. It's the same thing in every predictive analytics system. When the model actually executes in real time, we know whether or not our prediction worked. And we can compare our predictions with the actual outcomes over time. It's never going to be perfect. Some models have a 55% prediction rate, and that's considered to be good. Some models have a 95% prediction rate, and that's considered to be good. There are all sorts of ways that we can compare the performance of our model with benchmarks and then track that performance over time. And when our model goes beyond the bounds of what we consider acceptable according to these measures, we go through this entire process again. We go back to the big data, the crude data. We refine it again and get all the new data that's been pouring into that crude data store over time. We refine it again. We give it back to a data scientist. We might keep things simple and just automate the process and have a system do what the data scientist did last time and rebuild that model. That works for a while, but not forever. We might actually bring in another data scientist again to go through that entire cycle, rebuild a new predictive model, and deploy that out to the system. How often that happens depends on the industry. As little as a couple of years ago, people were telling me it was routine to refresh a model perhaps every year, maybe every 6 months, maybe every 3 months. I've seen plenty of applications today where models are refreshed daily because the edge that people get from the new data that's pouring into the system in terms of the power of the predictions is just what makes those systems competitive. So I promised I would explain the buzzwords here, and the main buzzwords I've been using are big data and real time. And people ask me all the time, what does that really mean, big data and real time? And the whole point of this presentation is to tell you that it depends. And it depends where in the process you are, what those things actually mean. Now, when we're at the crude oil phase, the unstructured data phase, this is when people talk about big data, this is usually what they mean. And when people talk about petabytes or even exabytes of data, they're not talking about the data that we use later down in the process. They're talking about that crude oil store. This massive, messy, unstructured data can indeed be very, very large indeed. And doing anything with this data, I put minutes to hours, sometimes it can be days just to extract data out of those systems. So it's not really real time, but we've got to go through that process, as I mentioned earlier on, every time we need to refresh the model. So we want to cut that down as much as we can. When it comes to the data scientist, building the advanced analytics model, the predictive analytics model from the structured data store. Data is much smaller by that point. We've done a lot of refinement, we've done a lot of distillation, but typically it can be in the gigabytes area, sometimes into the terabytes. And when it comes to a data scientist working with that data, it can be hours sometimes just to fit a predictive model, but using those modern systems that I was talking about, we can cut that down into minutes a lot of the time and allow those data scientists to iterate more and build better predictive models. Now we're transitioning out of the the big data phase of things and more into where real time becomes important. Because when we deploy these models into a real-time environment, think of a web server that's sitting behind that website that I showed you at the very beginning, that's responding to all those people that are visiting that web page and generating the ad that you saw on that screen. The amount of data we're talking about isn't great. It's probably best expressed as a rate, based on the number of people that are visiting the site at once. It might be megabytes of data when you collect, say, 100 people, 1,000 people simultaneously visiting TechCrunch. But the scoring system that goes from the data it knows to generating through the scoring rules the particular prediction, that's got to operate really fast, milliseconds type of operation, to be able to support many, many simultaneous requests that can come through the system. And then finally, at the consumption layer, we're now at the realm of one individual sitting at one PC visiting one website, or one individual holding a mobile phone using a mobile application. At this point, big data is not very big at all. An individual doesn't generate that much data in a real-time event that's used in that scoring process, maybe kilobytes of data, typically. And from the point of view of that individual, real-time just means fast enough that things are working nicely. Seconds, I click on my application, boom, I get a response. That's the kind of real-time response that people are getting when you have a millisecond response at the deployment layer and these types of processes at the big data layers. So at this point, I wanted to give you a little bit of a demo. You saw some of this demo in the keynote this morning from the predictive maintenance aircraft. I also promised that I would talk a little bit about R, and this seems like it might be a good time to do that, because in addition to real-time and big data and predictive analytics being a common thread amongst all the examples and applications I've shown you today, the R programming language has been used in all of them to generate the predictive language. So I thought I would just give a quick shout out and explain what R is for anybody that might not be familiar with it. It is the most widely used data analysis software used by data scientists, more than 2 million around the world, to build the types of predictive models that I've been demonstrating to you in the talk today. I've been using it myself for more than 15 years. The reason why I gravitated towards it is because it's really the most powerful statistical programming language out there. I talked about all those different models, k-means clustering, gradient boosted methods. All those are built right into R. I don't have to go out and find them anywhere else. So I have a lot of power to try and test and compare lots of different models so I can get the best predictive power at the end of the day. We haven't talked a lot about visualizations in this particular talk, but we saw some great ones earlier on in the keynote. It's a personal passion of mine, and R is very, very good at creating very beautiful and unique data visualizations. In fact, if you visit the New York Times website or you flick through the Economist magazine, a lot of the charts that you've seen in there were actually generated using R. R has been growing very, very rapidly. It's just been so many more users coming to use R, and part of that is because of the data science boom. There are so many companies that are looking to hire data scientists to build exactly those predictive models that we saw in phase 2 earlier on. Data scientists at university learn R. That's what they're taught with because that's where all the research is done. And so companies are building a lot of R practices within their data science groups so that they can bring in these data scientists that have been newly minted out of university. So a lot of growth about R in the community, and therefore a lot of growth with R in companies. And equally importantly, R is open source. There's a thriving open source community working with R that extend R to add all of those new models and techniques that I mentioned before. And also it's the leading edge of analytics research. If you're really at the forefront of needing to make predictions better than somebody else in your industry, it sometimes makes sense to really go to the latest research. And professors and researchers actually build all of those new models and techniques using R and then making them available for free into the open source community. So you have access to the very leading edge of analytics research if that's what you need to compete. Microsoft has been a great supporter of open source R and the R project, and has also created its own enhanced open source R distribution. It's exactly the same as the open source environment, so you have access to all that leading edge research in the open source community, but we make it faster by making it multi-threaded. And for our enterprise product, Microsoft R Server, we add some of those big data techniques that let you run those big models directly within SQL Server or directly within Hadoop, again, to cut down that data science cycle time. If you'd like more information about R, you can have a look at mran.microsoft.com, which is the Microsoft R Open website, or my colleague Joseph Ricketts, sitting in the front here, will be giving a tutorial on R tomorrow morning where you can get a good in-depth look about what R can do. So that's my little diversion about R. Let me move into a demo. So we saw part of this demo in the keynote this morning, and the basic idea here is that I'm an operations manager at an airline. I don't know if you've ever been sitting on a plane, you're ready to go off on vacation, you're about to take off, and suddenly there's that ding, and the pilot comes over the intercom and she says, look, I'm sorry, but we've got a light on the dashboard here, we've got to get the maintenance team in and check it out before we can take off, and before you know, you've been sitting there for 90 minutes and you've missed your connecting flight. Happens to me all the time. This is a consequence of maintenance issues arising that just haven't been anticipated by the airline. If only that airline could predict ahead of time that this particular aircraft, as it lands, there's a good chance that even though there's no light on the dashboard yet, there's going to be one soon. So do some preventative maintenance on that aircraft. Maybe we can do it on the field, maybe we can bring another aircraft in from the system and make sure there's no delay to the passengers and then keep the network working. And we have a Power BI application to do exactly that. So let me click into it here. You can actually try this yourself. It's on the Power BI website. Just go to the Solutions section and go to Airline. I'm going to open up the Power BI report. A little bit of information there behind that. Just it's very small, I know. You won't be able to see that very well, but on the top right-hand corner, that's an example of the data that's coming into the system. You've heard of airline black boxes. They're not used just in crashes. They actually generate real-time telemetry data as the plane is flying, which goes back to home base in the operations center. I think a 787 these days, on a typical flight, will generate 1 terabyte of sensor data, just from all the sensors that exist in the airlines and the engines and the wings and so forth. But we can use that sensor data and then compare it with historical events where we've had unexpected maintenance issues and see where we can find patterns in that sensor data that will lead us to predict that a maintenance issue might be coming up. So we have an application, again, focused towards the operation manager to do exactly that. You can see my fleet there on the left-hand side. I've got about 20 or so planes in my fleet. They're color-coded according to the likelihood of a maintenance event upcoming. The red ones mean there's a very high likelihood of an unexpected maintenance event soon. The yellow ones are low alert. The gray ones, there's no alert right now. Let's click into one of those. I'm going to click into 1ABCK, that's its tail number. And you can see it just goes down to a 1 there, I'm just showing that one plane. And you can see the messages that have come in through the system that are generating that alert. You probably can't read that, so let me just zoom it in a bit. It's not going to make it too much bigger, but I'll see if I can do that. Left click, there we go. So I've got an anomaly message coming in from the engines saying that there's a significant engine second stage anomaly. That's a pretty good indicator that something might be wrong that we need to do something about. There's a maintenance message that's being generated by the system that indicates there's a significant likelihood of a maintenance event. We've got a forecast from our machine learning model that tells us that in addition to that maintenance event, we're likely to get an anomaly from the bleed air system. And finally, there's a recommendation being generated that fuel consumption is likely to increase, and we should do some general maintenance. So the big question there is, where do these messages come from? Where are the models that are actually generating these alerts and messages in the system? And as you might guess, of course, those are predictive models. And let me give you a bit of insight into how those are generated. So this is just part of a wireframe diagram coming out of Microsoft Azure ML Studio, which is beginning with all the sensor data that is coming in, all of the sensor data that has come in from previous flights, combined with records of maintenance events that have happened with all those previous flights. And you can see it's a combination of built-in Azure machine learning models and also models that are coming out of the R system. The data scientists tried lots of different techniques and then picked the best one to actually deploy into the production system. So just to summarize what you can see here, you've got those historical black box sensor records and the maintenance events for many aircraft over several years. We train and compare several different predictive models to predict when those maintenance events happened, and then we generate from that system those scoring rules which will predict those likely maintenance events. And you saw those come up on the screen in the dashboard. So that's the training phase. When we go to the modeling phase, when we go to the scoring phase, in real time, as a plane is in the air, we have black box sensor data coming into the operations system. We're going to combine that live black box data with those scoring rules that we generated in the previous screen. And then we have those rules that will generate those maintenance alerts in the Power BI dashboard if those rules are exceeded, thresholds exceeded, and so forth. So that's just one example of building a predictive analytics application. Microsoft has tools that exist right through this process to help you. In the crude data and structured data part of the process, we of course have Microsoft SQL Server 2016 with the built-in analytics and HD Insight. For the data scientists that are using that data to build those predictive models, we have Microsoft R Server, and we have just recently released integration with Visual Studio for those data scientists to be able to use the R language to build those predictive models using Microsoft R Studio. When it comes to deploying those predictive models, you saw just a moment ago a screenshot from Azure ML Studio, which not only provides machine learning techniques, both built-in and from Python and from R, but the ability to publish those predictive models as web services, which can plug into the real-time operations suite. And that's part of the entire Cortana Analytics suite, which provides platforms and services right through this stack to build applications like the one you just saw. And finally, for the end user consumer who's going to be interacting with these predictive models, just a couple of examples we saw here in this talk today were Power BI, where we can interact with the dashboards, and as we saw in the keynote this morning, using Microsoft Excel as the consumption tool for the results from these predictive models. So let me just wrap up with one little parting thought. As I mentioned, I've been working with predictive models and predictive analytics for a long, long time. It's really exciting for me on a very personal level that we're really in a golden age when it comes to predictive analytics. I've seen the research over the last decade, I've seen the promise, but it's only been the last couple of years that we've really seen this realization of predictive models touching every phase of our life and doing things that almost seem magic based on being able to predict with data. And I think the reason why we're entering this golden age is because for the first time we have the confluence of 4 factors that are necessary for building real-world working predictive models like I've been showing you today. The first is the advent of big data. I'm not one of these people that says you don't need models, you just need data. I think you do need models, you do need data scientists, but having more data definitely helps. And the more data you have in many instances, the better these predictive models. And now that we have the technology to efficiently and especially cost-effectively store these massive volumes of data and all these new data streams that we're generating, we have such a rich source now for building predictive models. And then, of course, we have the computing infrastructure. The ability to spin up the computing power that's necessary to not just work with these massive amounts of data, but the very intensive computational tasks that are associated with the data science process of building these predictive models. We have these cloud computing resources to do that. And then in the real-time operation, having web services, predictive models just out there in the cloud available to a mobile phone application has really changed the game in terms of the applications where we can put predictive applications in. And then, of course, there's the rise of data science itself. I think I grew up as a statistician. We evolved into data scientists because we've figured out the actual practical processes for making these models and techniques work in real-world applications. And the research continues. Data scientists have really advanced the game of understanding how to put all the pieces together when it comes to building predictive analytics applications. And a lot of that is built on top of open source. There's such innovation that's happening in the open source world when it comes to predictive modeling and data visualization and operations around models that it's only with all of these four factors together that we're able to do the magic that we're able to do now with the predictive models. And I hope you do some of the same magic yourself. Thank you. I believe we do have a couple of minutes for questions if anybody has questions. Yeah, we have a question here in the back. I don't know if they have the mic in the room, but... Mm-hmm. Mm-hmm. Yep.
So when you're scoring in real time,
Mm-hmm.
you probably need to have access to all those data sources
Yep.
as well.
Mm-hmm.
So is there some kind of integration that goes into the API
Yeah.
that scores it?
So the question was, if we're building a predictive model like this on a website, we're taking data from lots of different sources together. I think your question was, is there a process in the real-time environment to be able to connect back to those original data sources? And the answer is no. The reason the answer is no is because part of the whole design of this process, if you will, is that when we get into the real-time environment, we no longer need the links back to those original data sources. Those scoring rules, that little sort of square I had, that embodies everything that you've learned from all those data sources into a relatively simple piece of code that can run in a real-time environment. That's what makes the real-time part work. That's why we can make these decisions or make these recommendations in milliseconds. It's exactly because we don't have to go back to the original source data to be able to make those predictions. Thanks for the question. Do we have any others? Yeah, over here.
Yes, you talked about consumption in the context of web applications.
Mm-hmm.
I'm curious about the application of predictive models to IoT systems.
Mm-hmm.
So can you just talk a little bit about the considerations, maybe the risks around connecting the output of a predictive model to something like an IoT system where we can change the behavior of that IoT system or some sort of controller on, for example, a data factory?
Okay. So the risks of connecting a predictive model to an IoT system, I think the point of your question is when we've closed the loop, we've made the prediction and then some kind of action is taken, either a manual action from the flight operation or more often an automated system that's going to make a change to the environment based on that prediction.
So how do you manage the sort of maintenance of the predictive models to make sure they don't go off?
Yeah. So first thing is test. A lot of the process of, I didn't go through any of this in my talk, but a lot of the process of deploying these models is actually being able to test them in that real-world environment, especially when you have those connections. But I think that brings back to the criticality of being able to continually monitor the performance of predictive models. That was the fifth step in my 5 stages that I gave you earlier on, is that it's not just a matter of coding up and deploying this predictive model. You've actually got to monitor it as it runs in the field and make sure that, especially as you're making those changes in the real-world environment, that the predictions of that model are still matching with the actual outcomes that happen. I think the danger that you might be referring to there is, getting into a feedback loop from an IoT system. You make a change that causes a change in the data, blah, 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 blah. But because we're already because we're already divorced from the historical data, that will be tripped up by the process of comparing the performance of the model in real time with the actual outcomes, because those scoring rules are not actually influenced by the real world data at that point. And so there's no possibility of a feedback loop as long as you're monitoring. Okay, thank you. All right, well, I think that's probably all the time we have, so thank everybody for attending today.